Welcome back. I hope you're refuelled and refreshed and have laser-like focus for this last section. We're going to discuss two final types of 3D printing that both employ a laser to solidify the object they are making. In the first method, which is known as Stereolithographic or SLA printing, objects are made from a resin and a laser is used to photo-cure molecules together. The resin contains small molecules known as monomers. The resins we use are usually based on polyethylene glycol diacrylate or PEGDA. The diacrylate groups can react and bind together when they are excited by laser energy, although we usually add a photoinitiator to help speed up the process. Because they are small, the resins are usually liquids at room temperature, so the printer holds them in a tank. When you want to print an object, a laser is focused into the resin, which causes the PEGDA molecules to combine, creating a cross-linked polymer. As the polymer chains get bigger and bigger, they become solid. To create an object, therefore, the laser moves in a raster pattern through the resin, solidifying it to create a layer. Because the resin is a liquid, in this type of printing, the object is actually printed on the underside of the build plate. When the first layer is finished, the build plate rises and the next layer is printed. As ever, the final object is created layer by layer. Some examples of the types of printlets we make with SLA printing are shown on the screen. They are drug loaded with either paracetamol or 4-ASA. As you might imagine, the mechanical properties of the printlets are dependent upon the number of chemical crosslinks, which in turn is a function of the number of PEGDA molecules. We can weaken the printlet by diluting the resin with a low molecular weight polymer. Typically, we use PEG 300. Because PEG 300 does not have any diacrylate groups, it cannot cross-link under the laser. The printlets on the screen were made with varying ratios of PEGDA to PEG 300. When we measure dissolution rates from these printlets, we see that increasing the PEGDA content decreases the rate of drug release, because there are more cross-links as the PEGDA content increases, which makes it harder for the drug to diffuse out. Yet again, changing the formulation allows control of the dissolution behaviour. One interesting thing we discovered is that if we dilute the resin with water rather than PEG 300, we can print hydrogels. Some examples are shown on the screen, simply because I think they're really cool. We have done a lot with SLA printing, including printing a polypill that contains 6 different drugs and printing hearing aids. We have also developed our own SLA printer that uses the light from a smartphone to cure the resin. The final type of printing we will talk about is known as laser sintering. Here, a laser is used to heat particles up and cause them to fuse together. A schematic is shown on the screen. Much like the powder bed printer I mentioned earlier, a layer of powder particles is spread out. But rather than using an inkjet printhead to spray a glue, a laser beam is moved over the particles in a raster pattern. The energy in the laser heats the particles up, causing adjacent particles to fuse together. Again, the laser is used to create the first layer of the object before a second layer of powder is spread out, and the process repeats, exactly like the powder bed printing process we discussed earlier. Incidentally, the laser can be so powerful that even metal powder can be fused in this way. But we don't use metal particles in medicines. No one wants that sort of iron tablet. You will probably not be surprised to know that laser sintering produces weakly bound powder tablets, very similar to those made with powder bed printing, and so they also tend to be fast dispersing. On the screen you can see some of the printlets we have made with laser sintering. Because the laser beam has a very small cross-section, we can make structures with complex geometries. I showed you earlier how fast a Sprytam tablet disperses in water, so let's see how one of our printlets compares. Pretty good, I think you'll agree, and made at low cost in our own laboratory by an MSc student. Right, a couple of other points and then we are done. One is that you might be interested in how organs and body parts can be 3D printed. The answer is a combination of inkjet and 3D printing is used. A 3D printer is used to build a scaffold the same shape as the organ to be replaced. I think, to be fair, we are not yet at the point where we can print organs, but more simple structures, like ears, are doable. One beauty of 3D printing is that because it prints in layers, it can take data from medical scanners, like MRI images, directly, because these actually create images layer by layer and combine them to make a three-dimensional model. So the patient can be scanned and the data fed directly to the printer. Once the scaffold is ready, an inkjet printer is used to deposit cells, often stem cells, onto it. The cells are suspended in a bio-ink that maintains their viability and protects them through the printhead. The final point is that although there are loads of printers available on the market, none is optimised for the GMP needs of the pharma industry. So we developed our own. It's called the Medimaker and is made entirely from GMP compliant materials. It has interchangeable print heads, so can print in various ways, including fused filament and gels, but we haven't looked at those today. It's designed to be placed in a pharmacy and to be used by a pharmacist to print medicines for individual patients. You can find out more about it by visiting the website of Fabrics, which is the company we set up to develop pharmaceutical applications of 3D printing. I have put a link to our website below. That leaves us at the summary, which is that inkjet and 3D printing have many applications to personalised medicines. Clearly, it would be bonkers to suggest that printing will replace large-scale powder compaction as the main method by which tablets are made. It won't, simply on cost grounds. You have to find a niche that only a printer can fill, and then build a business case on that. Some that I think are feasible are shown on the screen. I hope you found our discussion of pharmaceutical printing useful, and you now understand the basics of how inkjet and 3D printers work. I very much hope that one day you'll find yourself in a lab with a printer developing new applications. If you enjoyed the lecture, please hit the like button and consider subscribing. It really helps promote the channel. There are more lectures coming up where I will discuss some of our 3D printing work, which I hope you will also watch. Otherwise, thank you so much for watching, and I'll see you again soon.